A photon is born in the fiery heart of a distant star a million light years away. It races through the freezing darkness of intergalactic space, slipping past the gravity wells and drifting clouds of dust. And after traveling for a million years, its journey ends where it strikes a single cell in your eye. For us here on Earth, that's a story with a beginning, a middle, and an end, a journey that took millions of years. But for the photon, that entire epic, a million years of cosmic wandering from our perspective, happened exactly in zero time. From photon's point of view, the instant it was created is the exact same instant it was absorbed. It experienced no journey, it crossed no distance, and it felt no passage of time. It was born and it died in the very same moment. This isn't a philosophical riddle, it's a direct consequence of the laws of physics that govern our universe. It's a truth so profound and so alien to our experience that forces us to ask a terrifying question. If the fundamental particles that make up our reality don't experience time or space, are time and space even real? Or are they just stubborn illusion we all share? Today, we are going to the edge of reality, to a place where time and space break down, to ask, what is universe really made of? To see how a million-year trip can happen instantly, we have to jump back to 1905. A young patent clerk in Bern, Albert Einstein, released a paper on special relativity. It rested on two ideas that sounded simple but changed everything. The first one is easy enough to swallow. The laws of physics are same for everyone moving at a constant speed. If you are on a perfectly smooth train and you drop a ball, that ball falls straight down, just like it would if you were standing on the ground. Simple. There's no special master reference frame in the universe, but it's the second idea where things get weird. Einstein proposed that the speed of light in a vacuum, the cosmic speed limit of roughly 299,792 km per second, is same for everybody. It doesn't matter if you are standing still or racing towards the light source in a spaceship nearly at the speed of light. When you measure that speed, the speed of light, you will always get the same exact number. Now hold on, this should feel wrong. We are used to adding up speeds. You drive at 50 kilometers per hour, you throw a baseball at 50. To someone standing on the side of the road, the ball is moving at 100. Simple, 50 plus 50. But light doesn't play by that rule. Turn on a flashlight in that same car. The person outside doesn't see the light moving at your speed plus its speed. They see it moving at exactly the speed of light. And here's the weird part. You sitting in that car also measure it moving away at exact same speed. This one rule cannot be broken. If everyone must agree on speed of light, then something else has to bend. And what bends is time and space. They're not solid, fixed stage Newton imagined. They are flexible, they stretch, they warp, and they depend on who's watching. My time isn't always your time. And that's our first clue to why photon doesn't experience time at all. To really get our heads around this, we don't need complicated mathematics. We just need simple thought experiment, the light clock. Imagine a clock made of two parallel mirrors. A single photon bounces between them. Every time it hits the top mirror, the clock ticks. If this clock is sitting in front of us, the photon travels in a straight path up and down. The distance is fixed, the speed of light is fixed, so ticks are perfectly regular. Tick-tock. Now let's put that clock on a spaceship flying past us, say at 80% the speed of light. From our perspective, the clock is moving sideways. For the photon to get from the bottom mirror to the top, it now has to travel a longer diagonal path, because the top mirror has moved by the time it gets there. Remember Einstein's rule, the speed of light is constant. We, the stationary observers, still see that photon moving at the speed of light. But we also see it traveling a longer distance for each tick. If speed equals to distance divided by time and the speed is constant while the distance has increased, there is only one possible conclusion. Time itself must have increased. From our perspective, the moving clock is ticking slower than our own. Time for that spaceship has slowed down. This is not an illusion, it's a real measurable effect called time dilation. Astronauts on International Space Station are moving faster than us, so their clocks tick ever so slightly slower. GPS satellites orbit at even higher speeds, and their clock still have to be constantly corrected for the time dilation. If they weren't, your GPS would be off by several kilometers every single day. Both voyagers are moving away from us at an astonishing speed, so its clock is running slower. The faster you move through space, the slower you move through time. So what happens when you push this to the absolute limit? We have seen that as you approach the speed of light, time dilation gets more and more extreme. But a photon isn't approaching speed of light, it is at the speed of light. It has no mass, so it travels at the cosmic speed limit, c. So what does math say happen at v equals to c? It gives a clear, unambiguous answer. At that exact speed of light, time doesn't slow down, it stops completely. For a photon, time doesn't pass. From its point of view, now we have to be very careful using this phrase. There's no before or after. A photon doesn't have a rest frame, so it doesn't experience the time the way we do. The moment it is born and the moment it hits your eye are, for the photon, the same event. A photon that has traveled million years didn't age at all. Its entire journey happened in no time. Now, relativity tells us that space is just as flexible. As you approach the speed of light, the space in your direction of motion contracts. This is called length contraction. From your perspective, the universe shrinks. For a photon traveling at the speed of light, this length contraction is total. The distance between its start and the end point compresses all the way down to zero. That million-year journey, from photon's point of view, the distance between the star and your eyeball was zero. No time passes, no distance is crossed. For a photon, the entire universe is a single point, experienced in a single instant. If your mind is spinning right now, good. That means you are paying attention. And we are just getting started. What we have discussed so far is agreed upon and experimentally verified physics. But this conclusion that photons are timeless and spaceless is a doorway to a much deeper question. If you are enjoying this trip into the bizarre nature of reality, help me out and hit that subscribe button. It tells the algorithm that big ideas are worth spreading. Now, let's get weirder. We have reached something profound. The very particles that carry light don't live inside time or space. That should make us stop for a moment. We usually picture space and time as foundation, the stage the universe is built on. But if the actors on this stage don't follow the rules, maybe the stage isn't as solid as we thought. This brings us to one of the biggest mysteries in physics. Our two best theories don't agree. On one side, you have general relativity, a theory of the very large. It treats space-time as a smooth fabric. Mass and energy bend that fabric, and we feel that bending as gravity. And we have tested this over and over. We have seen massive spinning objects, including Earth, twisting space-time itself. That effect has a name: frame dragging. On the other hand, we have quantum mechanics, which describes the world of the very small. It's a world that is grainy, probabilistic, and weird, where particles can be in multiple places at once. Both theories are incredibly successful, but when you try to merge them to describe the gravity of a single particle or the inside of a black hole, the math breaks and spits out nonsense like infinity or divide by zero. This tells us that our understanding is incomplete. We are missing a deeper theory of quantum gravity. And a radical idea in the search for this theory is that space-time isn't fundamental at all. It's an emergent property, a large-scale illusion that arises from a deeper, stranger, and fundamentally spaceless and timeless quantum reality. But what is an emergent theory? Just as the wetness of water is an emergent property of trillions of H2O molecules, a single molecule isn't wet. Maybe space-time is what quantum mechanics looks like at our scale. So if space-time isn't truly fundamental, what is it made of? What's underneath it? A growing number of physicists are exploring a wild idea: quantum entanglement. You may have heard of it. Einstein called it spooky action at a distance. It's when two particles become so deeply linked that measuring one instantly tells you something about the other, no matter how far apart they are. Now, this is going to confuse you. There's a bold idea called ER equals to EPR. It suggests that this spooky link is actually geometry of space-time. In other words, two entangled particles might be connected in a tiny wormhole, an Einstein-Rosen bridge. If that's true, then space itself may not be something that exists first. Instead, space could emerge from these quantum connections. The more of these two things are entangled, the closer they are. Not in ordinary distance, but in the structure of reality itself. In this picture, the universe isn't sitting inside a container, the universe builds a container. Our 3D world might be a hologram, a projection from a deeper layer of quantum information where distance, as we know it, doesn't even exist. Another radical theory called loop quantum gravity paints a different but complementary picture. It suggests that if you could zoom in on spacetime to the tiniest possible scale, the Planck scale, you'd find that it's not smooth at all. Instead, you'd see that spacetime is made of discrete, indivisible units, like pixels of reality. As per this theory, space is a network of interconnected loop, a chaotic structure often called as quantum foam. Time doesn't flow like a river, it ticks forward in indivisible steps. In this world, there is no in-between. The very concept of continuous space and time dissolves into a granular, more fundamental reality. Our smooth universe could be just a large-scale average of these quantum loops. This leads us to a fascinating, if speculative, new metaphor for reality, the blockchain universe. Imagine every quantum interaction, every event records a transaction in cosmic ledger. This act of creating an irreversible entanglement is what we experience as a moment of now. The past is simply the set of all recorded blocks on the chain, fixed and unchangeable. The future is an open space of all possible transactions that haven't happened yet. And the arrow of time is nothing more than the process of the ledger growing, one quantum event at a time. Spacetime emerges from the patterns of information in this cosmic data structure. So back to that question, what is reality made of? Our journey started with a strange fact about a photon. We saw how relativity forces us to accept that for light, time stands still and space disappears. But that wasn't the answer. It was the loose thread that, when pulled, starts to unravel the entire picture of reality. That thread led us from the established physics to the speculative frontier of quantum gravity. We have seen how space-time itself may not be fundamental, but an emergent illusion. An illusion woven from the spooky threads of quantum entanglement, an illusion built upon the pixelated quantum foam, an illusion perhaps best described as a cosmic ledger where the arrow of time is simply the irreversible recording of reality. We live our lives on what feels like a solid stage, the stage of reality, but the science is pointing towards a shocking possibility, that the stage of reality itself is woven from the actors, that our universe of location and duration is a grand-scale effect of a deeper, timeless and spaceless quantum world. The very light that allows you to see this world may not truly exist within it, and the thought is where the next revolution in physics begins. So what do you think? Is spacetime the bedrock of reality, or is it a beautiful illusion generated by something deeper? Let me know your thoughts in the comments below, and if you want to keep exploring the biggest questions in the universe, make sure you're subscribed with notification on. Thanks for watching.